Hello friends, welcome to my presentation on how to correctly calculate the transformer kVA rating. By the end of this video, you are going to understand the steps to size the transformer kVA rating and the adequacy checks that need to be carried out to ensure the correctness of the calculated transformer kVA rating. Okay, so what is a transformer? Electrical transformers are used in everyday life. A transformer is a passive electrical device that is used to increase the voltage level at the power generating station, which is step up, or to decrease the voltage level, that is step down, for electrical power distribution purpose. Transformer sizing is a very important step, and we must make informed decisions regarding proper transformer sizing and its impact on electrical system under different operating and loading conditions. Okay, so why is it important to size a transformer correctly? Well, it will lead to higher cost due to oversized transformer, conductors and circuit breakers in case an oversized transformer rating is selected. Also, a large transformer rating will result in higher fault level, assuming the same transformer impedance, which will require increased circuit breaker rating as well as an increase in the maximum interrupting current. And in case an undersized transformer rating is selected, it will create issues within the electrical power distribution system, including loss of load and voltage drop during starting of the largest motor may exceed the acceptable limits. Let us now get into the method to be followed for the transformer kVA calculation. The starting point of the transformer sizing is the load that will be supplied by the switchboard or the panel connected to the secondary side of the transformer. Now, peak load should be used for this purpose. Peak load is obtained from the electrical load schedule. We should not use connected load for transformer kVA calculation, as it will result in an oversized transformer. In case you are interested in understanding how a load schedule is calculated, please watch my video on understanding electrical load schedule. Link for the video is given in the description. So once we have the peak load, the transformer kVA rating is calculated as the sum of the peak load and the expected future growth. Now, future growth is normally considered between 10 to 30% depending upon what additional loads are expected in the future. Once we have calculated the transformer kVA rating, we need to carry out checks to ensure that the kVA rating is adequate. The calculated transformer rating should be checked to ensure that the overload during starting of the largest motor is within acceptable limits of 150%. Also, the transformer rating should be cross-checked for its capacity to start the largest motor, with the voltage drop at motor terminals restricted to within 15% of the nominal voltage. For this purpose, we need to consider all loads, including the future loads, as operating when the largest motor is started. And why do we need to ensure that the voltage drop at motor terminal is limited when the largest motor is started? Well, if the voltage drop at motor terminal is very high, the motor starting torque will be excessively reduced, as the motor torque is proportional to voltage square. And in extreme cases, this will result in failure of the motor to start. Also, the disturbance caused on LV networks due to starting of the large direct on-line motor will result in considerable disturbance to neighboring consumers. Let us now understand the transformer kVA sizing with a calculation. For our example, we are calculating the kVA rating of a 11 by 0.42 kV transformer feeding a 400 volt LV switchboard as shown in the SLD. The largest motor connected to the 400 volt LV switchboard is a 85 kilowatt motor. So first we need to find out the peak load of the 400 volt LV switchboard. Details of the continuous, intermittent and standby loads of the 400 volt LV switchboard are given in the table. So the peak load of the 400 volt switchboard is calculated as 100% of the sum of all the continuous loads plus 30% of the sum of all the intermittent loads plus 10% of the sum of the standby loads. Based on the formula, we arrive at a peak load of 1473 kilowatt plus 922.45 kVAR, which works out as 1738 kVA. Once we have the peak load of the 400 volt LV switchboard, we can now calculate the transformer kVA rating. The transformer kVA rating is calculated as peak load plus future growth. Considering 10% future growth, we have the transformer kVA rating as 1738 plus 10% of 1738, which works out as 1911.8 kVA. Hence, the transformer kVA rating is selected as 2000 kVA and the transformer percentage impedance is selected as 6% based on table 1 of IEC 76-5, which is the minimum impedance recommended for transformers with kVA rating between 1251 kVA to 2500 kVA. We now need to carry out the adequacy checks of the calculated transformer kVA rating. We shall check the transformer kVA rating with respect to overload and voltage drop when the single largest motor connected to the 400 volt LV switchboard is started. First, we'll carry out the adequacy check for overload. Data of the largest motor connected to the 400 volt LV switchboard is given in the table. The motor rating is 85 kilowatt. The running power factor is 0.85. Running efficiency is 0.947, while the starting power factor is 0.3 and the starting factor with dual starter is 6. Based on the motor data, we can calculate the motor running kVA as well as the motor starting kVA. The motor running kVA is calculated as motor rated kilowatt divided by power factor into efficiency, which works out as 105.6 kVA or 89.76 kilowatt plus 55.63 kVAR. Also, the motor starting kVA is calculated as 6 times the motor running kVA, as the starting factor with dual we have considered for this motor as 6. So we arrive at a motor starting kVA of 633.6 kVA, which is equivalent to 190.07 kilowatt plus 604.4 kVAR. To check the overload on the transformer when the largest motor is started, we will first calculate the total base kVA before starting of the motor, and to this value add the motor starting kVA and arrive at the total transient load during motor starting. Using this total transient load, we will compare it with the transformer kVA rating to calculate the transformer overload during starting of the largest motor. So we had earlier arrived at the peak load for the 400 volt LV switchboard as 1473 kilowatt plus 922.45 kVAR. Therefore, the total base load considering 10% future load is 1620.3 kilowatt plus 1014.7 kVAR. Therefore, the total base load before starting of the largest motor, that is when all the other loads except the largest motor are running, is total base load minus the motor running load, which we arrive at 1530.54 kilowatt plus 959.07 kVAR or 1806.21 kVA. Therefore, the total transient load during starting of the largest motor is the total base load before starting of the largest motor plus the motor starting kVA, which works out as 1720.62 kilowatt plus 1563.47 kVAr, which is equal to 2324.86 kVA, which is almost equal to 2325 kVA. Therefore, the transformer rating, which was selected as 2000 kVA, the overload for that is 2224.86 divided by 2000, which is 116%. As per table 4 of IC 76-7, transformer can withstand an overload of up to 150%. Hence, the rating of 2000 kVA transformer is acceptable. We shall now check the transformer kVA rating with respect to the voltage drop during starting of the largest motor to ensure that the transformer kVA rating is adequate. For this purpose, we shall calculate the impedance values of the source, the transformer, motor and the base load. Cables have been neglected for our case to keep the calculation simple. So in our example, we can see that the source impedance is equal to 0.127 ohm. The transformer impedance is 0.06 per unit. For the largest motor, the motor impedance when running is 1.52 ohm and motor impedance during starting is 0.25 ohm. And for the base load without the largest motor is 0.0886 ohm. Considering the base MVA as 1 MVA, we have base impedance on the 11 kV side equal to kV square by base MVA, which is equal to 121 ohms. Also, the base impedance on the LV side equal to 0.16 ohms. Now, per unit impedance of the source works out as 0.00105 per unit. Per unit impedance of transformer ZT is equal to 0.03 per unit. Per unit of motor Zm is equal to 1.57833 per unit. And per unit impedance of the load ZL equal to 0.54367 per unit. Considering Z1 equal to sum of Zs and Zt which are in series, we have Z1 equal to 0.03105 per unit and Z2 as sum of Zm and Zl which are in parallel, we have Z2 equal to 0.40438 per unit. Let us now consider V1 is equal to voltage at impedance Z1 and V2 is equal to voltage and impedance Z2. Therefore, voltage drop at the bus is equal to V1 divided by V1 plus V2, which is equivalent to Z1 divided by Z1 plus Z2. Based on the above, voltage drop at the bus is equal to 0.0723 per unit or 7.23%. As we have not considered the voltage drop in cables, therefore the voltage drop at bus is equal to the voltage drop at motor terminals. Therefore, voltage drop at motor terminals during motor starting is equal to 7.23%, which is within acceptable limit of 15%. We can therefore conclude that the transformer kVA rating of 2000 kVA has been selected correctly with respect to voltage drop during starting of the largest motor. Therefore, to summarize, to calculate the transformer kVA rating, we need to first calculate the peak load of the switchboard, which will be fed by the transformer. Then we need to add the future load, which is between 10 to 30% to the peak load to arrive at the transformer kVA rating. The next, higher standard transformer rating should be selected and the transformer percentage impedance should be selected from table 1 of IEC 76-5. Once the transformer rating has been selected, we should carry out the adequacy checks to ensure that the kVA rating is correct. The overload check should be carried out to ensure that the overload is within limits during starting of the largest motor connected to the switchboard. Overload should be within 150%. Voltage drop during starting of the largest motor with all other loads connected, including the future load, should be checked. Voltage drop at motor terminals should be restricted to 15% of the nominal voltage. This concludes my video on how to size an electrical transformer correctly. Thanks for watching. I hope you enjoyed this video. Let me know in case you have any questions. If you would like to see more such videos on electrical topics, please subscribe to my YouTube channel